Hello, my name is Nathaniel Jones, and I'd like to thank you for joining this webinar, Designed for COVID-19 and Beyond, New Use Cases for Computational Fluid Dynamics and Multi-Agent Simulation by Andy Harris, Nastaran Shah-Mansouri, and Reese Goldstein. This webinar is hosted by the IBIPSA USA Research Committee, with the goal to share new ideas from research to the building simulation community. If you have any questions during this webinar, please type them into the chat window. At the end of the 40-minute presentation, I will unmute our audience on Zoom for discussion with Andy, Nastaran, and Reese. Next slide, please. AIA Continuing Education credit is available for attending this webinar. Please email info@aiaeb.org with your AIA membership number to receive credit for attending today's event. And now, I'd like to introduce Andy, Nastaran, and Reese. Thank you.
Great, thanks, Nathaniel. I'm Reese Goldstein. I'm here with Andy and Nastaran. We're representing sort of a larger team effort from Autodesk Research. And what we're going to talk about is our goal is to apply building simulation to COVID-19. We're going to explore possible ways that computational fluid dynamics and multi-agent simulation could be used to help designers create safer environments for people in the face of COVID-19 and future viruses. Partway through this presentation, the scope is going to expand. So we're actually going to talk about some applications beyond COVID-19. What we really want to do is we want you to think about the different possible uses for CFD and multi-agent simulation, different use cases for highly detailed simulations in general. But we'll start with design for COVID-19. Okay, so the question is, why do we want to use simulation for COVID-19? Or to put that a different way, why couldn't we just use simple rules like the 6-foot rule, keep people 6 feet or 2 meters apart, or just put plexiglass around all workstations? Well, here's why there's issues with these simple rules. So here's some excerpts from a paper in the National Academy of Sciences, and I'm just going to highlight the key points here. So the 6-foot rule, it says, offers little protection from pathogen-bearing aerosol droplets. Yes, it protects you from ballistic droplets. It doesn't protect you from the aerosol droplets that mix throughout a space. And then they give an example of a choir practice where 53 attendees were infected. Not all of those 53 people could have been within 6 feet of the contagious individual. And there's more, and there's other, many other examples. There was actually a bicycle gym near where I am. I'm in Toronto, so is Nastaran, and he's in the UK. But there was a bicycle gym near Toronto where they followed all the guidelines. They kept the bikes 2 meters apart. They did what they were supposed to do. And what was the result? About 40 people got infected in the space of a week. So, okay, so how about plexiglass? Well, there was actually an office at a high school near Boston where they did put plexiglass around every desk. But again, the coronavirus just swept through. And later they puffed smoke into the room to see what was going on. And they actually came to the conclusion that the plexiglass may have actually increased the risk. It may have increased the risk by impeding airflow. Now, none of this is to say, of course, that there's anything wrong with those rules. That the 6 foot rule might be a perfectly fine rule, but the issue is relying solely on those rules. And the alternative to that is to really try to understand what's going on in each type of space. And the way we can do that is with simulation. So that's the motivation for using building simulation for COVID-19. So with that, here's the outline of our talk. We're going to present 3 projects. The first 2 are going to be on CFD. The next one's going to be on multi-agent simulation. So we're each going to present one of these projects that explores new uses for these simulations. And with that, I'm going to turn it over to Andy Harris to present the first project.
Thanks, Reese. So I'm Andy Harris. I'm a senior manager at Autodesk Research. I work across a range of industries, focusing on developing solutions for very challenging problems that our customers face. I've got a background in simulation, and in this talk, I was working closely with an architect, and we were looking at how we can use CFD to inform the design process of this enclosed outdoor space at this restaurant. So we wanted to try and reduce the risk of spread of COVID-19. So one of the big challenges we had with this outdoor space, and the reason why it had to be enclosed, is because of the buildings around it are quite high, and it's not quite an alleyway, but the courtyard had a lot of gusts of wind. It was very uncontrolled air. So we really wanted to control the air, but also have a really high air change rate within that space, around 20 air changes per hour we were aiming for, to try and extract as much air out of there as possible without it being uncomfortable. So if you move to the next slide, Reese. So the architect had a couple of initial design concepts. We had this idea where we were looking at feeding the air in from the outside, going underneath these transparent walls, and then it would go up and out through the roof. We looked at a couple of different designs, and we were looking at potential configurations of extraction systems or natural ways of the air to kind of come out of that space. But one of the challenges that I could see immediately from this, and you can kind of see it in some of the images on the right, is there's a wall actually along one of the sides. And if you were to reference that on the images on the left, that's actually along the top left edge. There's actually a wall across there which prevents us feeding any air in there, which immediately, to somebody who's familiar with simulation or airflows, would think actually we might have a challenge in those areas around that wall, and we'll look at that a bit further on. So if you go to the next slide. So this was design option A, so the first one that we saw previously. This one had some extraction fans in there, just 6 extraction fans, and then the rest of the outlets were just open to space. So between the extraction fans, it was closed. So we've got 2 fans on a closed wall, and then an opening, and then 2 more fans, etc., etc. That really didn't help with guiding the air out from the room. So you can see on the streamlines on the right-hand side, there's a lot of areas where there's actually no streamlines, like that bottom corner that you can see, and the left corner that you can see. That means there's no air. There's no air changes happening there, and that's because we're not guiding the air properly. So what we did is if we go to the next, there we go. So now we can see what we've done is we've closed off all the openings on the roof, and we're only relying on the extraction fans. So this forces the air to always be feeding from underneath those walls. So now we can see we've got a much bigger amount of air going through the space, and it's going through all of the space, which is a really good start. So if you go to the next slide, we can look at the next design option. So the next design option, all of these chimneys on the roof have extraction points, and all the air again is coming in from the sides, getting really good air changes in that space, which is a really good start. But then the next thing we really want to look at is what is going on with the air in that space. You know, it's all well and good having the air coming in and getting lots of air changes, but what we don't want to happen is to see lots of air going across multiple tables, because then potentially one person could start to infect other tables around them. And it could be that the airflow is contributing to that problem, and we don't want that to happen. So the next slide, please. So this is the diagram just showing that the air is coming in from the sides. We have that issue with the wall on the roof, so that wall on the top of that image. If you go to the next one. So really, this is a problematic area. So in order for air to get into this region, it has to cross from the tables that are around the outside. So we had to kind of think a little bit how we can kind of resolve that issue, help air get into that space, but we didn't have the luxury of being able to feed the air from underneath. That would be an obvious solution, feed the air from underneath the room and come out through the top. We had to keep feeding it in from the sides or potentially from the roof. So if you go to the next slide. So this shows the air problem that we had. So each of these images is kind of a snapshot of the air coming out of each of those chimneys. So for example, in the top left image, we're looking at the air coming out of that bottom right chimney. And you can see that even where the air is being extracted from the outer edges, where it's close to the inlet, it is actually still being, the airflow is still being attracted into the center of the room because there's no air feeding that. We've got extraction in that space. And it gets worse when you start to look at some of the ones like in the bottom left image, where we've got extraction at the top center. So we're right along the middle of that wall that we saw on the previous slide. All of the air is now crossing from the outside of the room into the center of the room and then up out through that chimney. So it's really it's not a very good situation to be in, really. It's going to potentially spread infection within that room. So if you go to the next slide. So back to that diagram. So that's the problematic area that we've marked in purple in the middle. If you click again. So what we looked at is how we could potentially relieve that issue by allowing air to come in through the center of the room. So we have multiple inputs of air. The air can come in through the roof at the center and coming through the sides of the walls, but it's still extracted through those chimneys. Now, immediately, this is very interesting from a simulation point of view, because potentially some of those chimneys might actually start to recirculate with the opening in the middle of the roof. So we wanted to look at that very carefully to see if that happens. So if you go to the next slide. So this is an image just showing what that area could look like. You know, we wouldn't put seating in the middle there because we know it's an inlet and we don't want air coming across tables from the inlet would then go across other tables to an outlet. So we looked at that as kind of a courtyard in the middle where nobody would sit, but they would sit around the outside where the inlets are. Go to the next slide. So this, in order to model this, we had to look at a slightly more complex CFD model. And again, that was particularly looking at potentially any air kind of recirculating through that opening in the center of the roof. So you can see that blue box on the right is actually our air volume for the CFD model. And then within that, on top of each chimney, we have a fan modeled that's extracting air. So it's extracting air from within its own air volume. So that would then allow, and if any issues with recirculation were to happen, it would allow that to happen. So next slide. So that just shows the streamlines. Again, we're getting really good air changes in there. You can see most of them, particularly on the left side, you can see a lot of the streamlines are going up to the top of the air volume and they're not recirculating down. However, there's something slightly interesting going on to the right of that, which we can isolate and look at a bit more. If you go to the next slide. So that image that you're looking at now on the right is showing that we're getting recirculation on that chimney. One or two of the others showed the same. We did a similar modification to the design to correct that, which we'll show a little bit later on. But this one was the worst one. It was recirculating back down into through the opening in the roof. It was feeding itself. It was feeding other outlets, which means then it's actually crossing other tables, which is not a good thing. So we had to look carefully about how we could fix that. So we go to the next slide. So these, where we have the air coming in from the outside, we've got good feed of air to the tables around the outside, around the outside edge marked with the green boxes. If you click again. And then we have most of the air is being for these other outlets. These are the fans marked in the green box as well, is being fed through the fed through that center opening in the roof. However, a little bit of the air is actually feeding some of the other chimneys, which is absolutely fine for it to do that. So that worked okay. If you go again, if you click, it should show the problematic chimney. That was the main one that was causing the recirculation. Click again. Great. So that chimney, if you just click once, Reese, we modified the design of that chimney, which we just marked into the blue arrows there. So the blue arrows just appeared and that chimney, we just raised it up. that was the one thing that kind of stood out to me from this chimney compared to the other chimneys, which didn't have the recirculating issues, is this chimney was a bit too low. And that meant it was a bit too close to the outlet, but also by raising it, and we raised it, we reduced the opening size, which meant that we caused the velocity at that opening to increase, which means the air is getting propelled further away from the roof of the building before it can then be caught and recirculated back. So if you click the next slide. So if you click again, you should see that chimney change. So there we go. Now we see the chimney's gone up and the opening's got smaller. So if you click again. So now we've remedied that issue. That chimney is now not recirculating. The air is coming out at sufficient velocity and at sufficient height that it is able to clear the pressure that would draw it back in through the opening in the roof. So if you click again. So this is the issue we faced before. We had a lot of air, and we're only looking at the air coming in through that outlet that was causing the problem. The air was coming back in, feeding, and then feeding in through the roof opening and then out through those other fan extraction points. So it's causing a lot of problems in that space and would contribute to the spread of COVID. And then if on the right-hand side, we're looking purely at the air going in through that opening. So we're kind of looking at it two ways. We're looking at the air coming in through that opening in the center of the roof. And we can see that it's mostly being fed from air from the environment, but also from that recirculation from that chimney. We click again. So this is the situation now. So the air is coming in through the center opening. It's going out through all the chimneys. We're barely seeing any kind of recirculation. We can see a few streamlines there. So the majority of any kind of recirculation is now gone, which means really all the air in that space is fresh air coming in. So next. Okay, just to conclude from mine before we move on to Nastran. So this was a temporary outdoor space that we looked at how we can influence the design of this space using CFD. Now, if we were to think about something a little bit more permanent in the future, and I mentioned this a little bit earlier on, feeding the air from underneath of the building would work pretty well. That might work better for a more permanent enclosure. Or if we had to look at this or other kind of spaces, particularly with looking at the risk of COVID-19, we might be thinking about how do we conserve energy as well in that space. And we'll be looking at how do we safely recirculate air in that space. And there's some really, really interesting technologies. There's some traditional technologies that use HEPA filters, but I'm thinking some of the more novel, unique technologies that use things like UV light in the HVAC system. These kind of things would work really well for potentially safely recirculating air in this kind of environment, in restaurants, in more permanent settings, or in offices or in other environments. So with that in mind, I'll pass over to Nastran.
Yeah, maybe. Thanks. And I'm just going to give a quick transition. Then we'll hand over to Nastran. But as you saw in that talk, where Andy presented a very detailed CFD study of a space, and we're moving away from the simple rules like the 6-foot rule or just plexiglass or things like that, and really trying to understand what's going on in a space. Now, in the next talk, we're going to shift our focus a bit. We're going to broaden the application and look beyond COVID-19. So the next talk is actually going to be about energy and comfort, but we still want to, the theme is still going to be the role that highly detailed simulations can play. So with that, I'll hand it over to Nastran Shamansuri.
Thank you, Andy and Reese. Hello, this is Nasran Shamansuri. I'm a principal research scientist at Autodesk Research in Toronto. My background is in computational mechanics and optimization. I'm glad to be here presenting our paper, which was published in 2020 for you today. The title of the paper is Investigation of the Potential Benefits of Optimizing Building Elements, Element Placement using Computational Fluid Dynamics. Next slide, please. Building construction and maintenance are responsible for more than 1/3 of global energy consumption. They generate directly and indirectly nearly 40% of total CO2 emissions. So energy modeling receives considerable attention. In addition to that, it's known that indoor environmental condition and thermal comfort can hugely impact the health, well-being and productivity of occupants. So a major challenge for creating sustainable and compelling buildings is to analyze microclimates within spaces and optimize designs with confidence. We need advanced fluid dynamics for that. If we go to the next slide. We need advanced fluid dynamics or CFD to understand building microclimates, and CFD has been widely used in different industries and such as automotive industry and aviation, and in different stages of simulation and design. CFD analysis has the potential to help building design and engineering professional as well to understand the flow properties over a refined temporal and spatial grid for different mechanical and architectural configurations. And as we saw in Andy's presentation, CFD can provide valuable information about health and safety of people in buildings. Next slide. Let's see what the problem is. The conventional practice for energy modeling is to use simplified energy models, where a uniform temperature is predicted for each zone. In these models, the exact placement of building elements such as supply and return vents, windows, and other elements have little impact on energy efficiency and occupant comfort. The problem is that a design based on conventional building energy modeling tools may conceal a poor overall configuration of elements, resulting in undesirable microclimates inside buildings. An alternative would be to combine building energy network modeling and CFD simulations. And the question that we want to look into in this work is that how much improvement in energy use and comfort could potentially be gained by shifting toward such high fidelity models. Next, please. The study is performed on a simplified indoor environment, similar to the building that we see here. It consists of a room with cooling, ventilation, and window elements. The location of supply cooling vents and return vents are systematically varied to cover multiple locations on opposite walls of the space. They are represented actually with the green and red dots on the walls in the picture. The CFD analyses are conducted on a total 36 supply return configurations, and the result for each configuration were obtained for 9 locations inside the building, representing different possible locations for occupants. They are shown by the blue dots here. The table these 2 tables provide information on the configuration and occupant locations that we used in the study. Next, please. Regarding the CFD analysis, to give you a little bit of background, it was conducted using a transient turbulent model called K-epsilon RANS. And the information about this analysis, mesh size, building, and the details about it are presented here, and they are also they can also be found in the paper. Next, please. Okay, now let's take a look at the results that we have. These pictures on the top row shows the airflow pattern in the room for two mechanical configurations when the supply turns on and works for 5 minutes. It looks like that the heavy cool air falls on the floor, and the airflow pattern is very much different for these cases. In the bottom row, the left video shows the three-dimensional airflow movement, and the right video shows temperature variation in the room at the standing height for 5 minutes. We see that the airflow has a complex pattern from the supply to the return vent. And the temperature varies inside the room, even at a specific certain height. Next, please. In this slide, we see the results for temperature predictions. So the temperature data for all mechanical configurations and the occupant locations are presented in the top figure. The values obtained for each mechanical configurations, including 9 occupant locations, are plotted with the same color symbol combination. They are basically the vertical lines in the figure that we see. And the plot on the top that we see shows all the temperature data obtained for the 324 combined configurations. The combined configuration that I'm referring to is a particular location where the velocity and temperature data have been evaluated in the simplified building for a specific supply and return configuration. The average value, which were obtained for 9 occupant locations, are also presented here. And with these black cross markers. And the data shows that the same forced air cooling input may produce location-specific temperature difference as much as 9 degrees. In the bottom right plot, and part of the picture is not shown here, but that's okay. The bottom right plot shows the data in an aggregated form. We see that the average temperature of 17 mechanical configurations are lower than 24 degrees. And the data shows the impact of mechanical configuration on the average temperature while the input energy level is kept fixed. The extrema and the probability density illustrates, we don't see the probability density here. They are presented in the paper. I hope the image is correct there. While an average temperature lower than 24 can be achieved, the temperature for several occupant locations could be higher than 24 degrees. And the temperature differences in different mechanical configuration can vary considerably. For example, more than 6 degrees for the configuration MC25. Next slide. Here we have a similar plot, basically, but for air velocity. And the horizontal line plotted in the bottom right figure shows an arbitrary velocity at 0.25 meter per second threshold, and the average velocities for all mechanical configurations are lower than this value. But for several cases, we see that the velocities at different occupant locations are higher than this threshold. And for 6 combined configuration, the velocity is higher than 0.6 meter per second. Next, please. This is the slide about temperature versus air velocity. The result obtained for all combined configurations are shown in the top right figure. And the data shows that the velocity and temperature data are mainly clustered in the left side of the figure, which means that occupants experience a low velocity airflow generally. But the data in the red zone shows that the lowest temperatures are cases with the highest air velocity, which are uncomfortable for occupants, basically. And we see that there is a trade-off between the goal of providing more cooling and the goal of having low air velocity. So one may argue that the best cases are configurations within the green area shown in this figure. Go to the next slide, please. Okay, in this slide, I'm showing the analysis and comparison of different mechanical configurations based on 5 categories. I will only discuss one case here. The case on the top row, which is the case with minimum average temperature. For this case, the supply is placed near the ceiling and in the middle section of the building, and the return is located near the wall on the opposite side of the window and the ceiling. Configuration depicted here has the lowest average temperature, and it is actually consistent with ASHRAE discussion on the outlet's location. However, its temperature difference, the temperature difference for this case is higher than 28 other configurations, and the average temperature of 13 of those cases are lower than 24 degrees. Next slide. Okay, to summarize, we discussed that in most building energy modeling tools, the exact placement of elements, have little impact on the analysis. The question that we wanted to answer was that when planning the arrangement of building elements, to what extent designer could save energy and improve comfort using CFD simulation. The result here showed that the placement can impact the air temperature and air velocity significantly. One occupant location or average temperature is not necessarily representative of a space thermal characteristics. Let's go to the next slide, please. Okay, what I want to mention is that this study was only the first step of for a series of studies, and this work only offers limited aspects of thermal comfort analysis. Whereas the study showed the large discrepancies in temperature, a more comprehensive model might instead predict large discrepancies in energy consumption as the system strives to meet a specific set point. And for future studies, conducting further sensitivity analysis, validating CFD results with experimental data, assessing the technological requirement and viability of incorporating CFD analysis into earlier stages of the design process could be explored. And there are currently good studies and research exploring these aspects. Thank you very much for your attention and time. I'll pass it to Reese again.
Great, thanks, Nasran. So I'll be presenting the last topic. My area of research is human behavior in buildings and multi-agent simulations. So that's what we'll be talking about now. Notice that in the previous 2 projects, we were looking at highly detailed airflow models, trying to capture how the air is actually flowing, what temperature it is at different points in space. But they also, both Andy and Nasran showed us more detailed occupant models than than what's normal for energy modeling, because you actually had specific locations of people either in the restaurant or in the office. But now we're going to go a step further. So not just occupants with specific locations, but real occupants. They move through buildings, they interact with a variety of objects in a building, they talk to each other, they engage in a variety of different behaviors and activities. And all of these can have an effect on the risk of COVID-19 transmission. So here we're coming back to COVID-19, and we're gonna ask the question: Can we make better predictions about the risk if we model detailed human behavior? So I'm going to go through this quite quickly. I should mention though that this was actually the work of a much larger team than just me. But so the goal here was to design a system that would help people evaluate the potential risk of virus transmission, and we're taking into account human behavior, longitudinal aspects, by which we mean different time scales, short time scales and long time scales, and an architectural or whole building scale. So you'll find lots of works that on COVID-19 that cover one or two of these areas, but not all three. So what we do is we take a 3D building model, we layer on human behavior, so you can see the humans moving around, and then on top of that, we layer on a COVID-19 simulation. And we'll go through these. Key layers. In the human behavior layer, we break that down into what we call context-related behavior and contagion-related behavior. So starting with the context, these are just the activities that people perform in office spaces, like or it could be any type of building, but in this case, we'll look first at offices. So they could be working, going to a meeting, etc., or traveling between them, or also operating the coffee machine or washing or what have you. So we do a simulation of this using what's called a discrete time Markov chain, which is actually the standard approach. You create a matrix of probabilities to transition from one activity to another. And so then how do you get these probabilities and parameters? Well, what we did here is we actually let the user input them all. So we've got this big interface where a person can actually fill in the individual probabilities if they want. They can choose the ranges of start and end times. They can define different workers. In a second here, you'll see the transition probability matrix again. Of course, you can also get the information from real data. So here's just a simulation of this behavior in an office space. So you can see the people moving through the office, and they start engaging in various activities. I'm going to move on to a restaurant environment, and here we actually collected data from the actual restaurant to learn about. We took notes to learn about the different types of behaviors that were expected there, and use that to create a simulation. And then, as well as that, there are a variety of behaviors that affect the virus transmission, like breathing, sneezing, coughing, and talking. Also, touching surfaces if you're looking at surface-based transmission. And all this was randomized. So moving on to the virus transmission, there's two types: air-based and surface-based. So for the air-based, we just use a grid, and each grid cell has a certain level of infectivity, which increases when an infected person breathes or coughs or sneezes into the space. We model the decay of the virus over time in a simple diffusion model, where the virus just moves outward to adjacent cells at each time step. So a very simple model, much simpler than the airflow models you saw in the previous presentations. As well as that, we also looked at surface-based transmission, and of course we learned later that that wasn't the biggest concern for COVID-19, but it could be a concern for other viruses. So there's still a use case here for simulation. So when occupants touch things, and an infected occupant touches the coffee machine, for example, they'll leave some virus on the machine that can get picked up by other occupants. So again, all these parameters are controllable by the user. We did our best to select default values from the literature, but that's a work in progress, because there's a lot of parameters that could affect the virus transmission. Oops, went too far. So just to show you what it looks like. Here you can see the virus diffusing outward from infected occupants. Notice how it just moves straight outwards. In this case, you can also see people moving around through the space. You might ask, well, what about adding CFD to this so that you actually have the virus moving in certain directions? I mean, that's something we're taking very seriously. So we're looking at how we could possibly combine CFD models with human behavior models. Obviously, it's a real challenge to integrate these techniques, but that's something we're definitely looking into. And so this work here is will be presented at the Designing Interactive Systems conference, which is just next week. That paper will focus on sort of the feedback we received from various stakeholders like business owners and health experts. It's also being presented at a talk at SIGGRAPH later in the summer. All right, so those are our projects. I just want to quickly acknowledge the other team members. These projects were all a team effort involving expertise in design, engineering, computer graphics, even human physiology. Let me single out Lindsay Wilkstrom. She's she's responsible for a lot of design work on the project Annie presented. Also, Bokyoung Lee. She was the lead author on the DIS and SIGGRAPH contributions for the multi-agent project. Okay, well, we hope that this introduced everyone to the potential benefits of using detailed simulations, the benefits both for COVID-19 and other viruses and for comfort and energy. All right, thanks.
All right, thank you very much, Reese, and thank you, Andy and Nastran. I want to remind everyone that AIA Continuing Education credit is available for today's webinar. Please email info@aiaeb.org to get that credit. And I want to give everyone a chance to ask some questions by typing them into the chat. While people are formulating their questions, I want to start out by asking one of my own. The COVID pandemic has given us a lot of opportunity to think about how buildings contribute to the spread of the disease. And I've been involved in a lot of those questions about how we can use mechanical systems to filter air, or how we can use sunlight or ultraviolet light to treat air. I wonder if you can comment on how those fit into simulation, and have you had the opportunity to look at them or considered how you might include them in some of the tools that you're using?
Andy, did you want to?
Yeah, I can happily start that one. Certainly from a simulation point of view, to kind of, to have the virions and the virions get recirculated through the HVAC system, and then you use a UV light to destroy them, that would absolutely work. But to put that in terms of simulation, in terms of what we've just seen that Reese has presented, that's further work that we would have to look at. But I would suggest that those kind of things, that HEPA filters, UV systems, all these kind of things are actually good things to investigate as potential solutions to enabling the benefits of the energy savings that you can get from recirculating the air, to kind of balance that with the fresh air input. But yeah, they're potentially pretty good solutions to actually investigate.
All right, thank you. I want to turn it over to Zoe. I think Zoe has a question, and Zoe, you can use your microphone.
Yeah, this is Zoe. My question was for Andy also. Did you have to consider trees in your CFD analysis? And how do you make sure to account for what an occupant places in the space? Is there kind of a balance to be struck between detailed simulation and more general assumptions?
Yeah, so there's no trees assumed in this space. We kept the model kind of the minimum amount that we'd need just to capture enough information about the direction of the airflow within the space. So the occupants in that space were assumed to be seated and also spaced out. So the key thing to note is each table had its own chimney, which meant that we kind of always directed the air from the sides of the walls up across the table and up through the chimney above them, which is something that we don't really see in a lot of current HVAC type systems. So if you look at a lot of HVAC systems, they have extractions at places that are potentially positioned away from people. So you end up with air having to travel large distances within the space, which potentially means it crosses multiple people. And every time you cross another person, it's an increased probability that you would then be moving virions within that space that then potentially could infect another person.
Thanks.
Okay, thanks. And we've got a couple of questions coming in from James. James, do you want to ask your questions? James, are you here? Oh, sorry, I need to allow you to unmute. James,
Thanks.
go ahead and ask.
Okay, thanks, Nathaniel. And also thanks for the presentations. They're all really interesting. So I have a question that I think applies to the first and the third presentation. That's how are you modeling the infectiousness of the pathogen in that agent model? And then have you considered modeling an infectious pathogen inside the CFD model, either as like a scalar model or as a particulate model?
Do you want to take that, or should I take that, Andy?
Yeah, I can answer the last part as well. So you go first.
Yeah. Okay. Yeah, that's a great question. So the modeling the infectivity of it. Certainly for the agent one, our intent or our hope was to really model the virus. We did want to capture as closely, as accurately as we could the actual risk, like ideally the probability that someone would get infected, given that the infected person was over here, they're in this location, the walls are the way they are, etc. You run it, try to actually get the probability out of that means going through the literature and really trying to find a lot of data for all different parameters. And one thing that's actually quite difficult is to figure out, like, how much virus can you intake before you have a high chance of becoming infected, because if you've only taken a little bit, you'll probably be fine. So we eventually decided to sort of defer that and just sort of just look at how much virus particles susceptible people take in. So how much virus healthy people breathe in, and then just sort of tracking the profile of that over time. So over time, a person takes more and more virus, but we still have to, I think, nail down, a good way of determining, when the person is like, when we can say this person is now infected. So it doesn't, however much more virus they take in, they're going to be infected either way. So that's probably future work to refine that. Sorry, Andy?
Yeah, so with regards to your question around scalar models and also particle models, so the answer to that, the simple answer is yes, we have looked at those. We're actually looking at not just these kind of restaurant spaces, we're looking at office spaces and things like that. And to some extent, they can get you quite far, but they don't get you all the way. So scalar models obviously can't, the scalar, which is the mixing of the fluids, doesn't go to a point where you end up with the droplets and the aerosols, which can then get carried by the HVAC system and carried away. They can be influenced by the HVAC system, but it just comes to a point where they just dilute and disappear, and you can't really see where the airflow is going. But they're really good to kind of see what's happening immediately around. So when I say somebody sneezes, you want to see what happens. Does it go over from the desk the person sat at? Does it go over the screen, the perspex screen in front of them, onto the desk in front of them? That kind of thing works quite well. With particle models, These are also really good to kind of look at where the air is flowing, a bit like the streamlines. But one of the downsides of them is they're not time dependent in the sense that they can't decay. They're not affected by humidity. They're not affected by sunlight or anything like that. And if you think about how these virions, which sit inside of a droplet or an aerosol particle, over time they evaporate and they get to a point where they're no longer active. And we're talking with a lot of experts about this to try and understand how the environment influence these droplets and at what point are they safe. And that kind of relates to some of the stuff that Reese was saying earlier about 6 feet apart. I mean, you even if you're more than 6 feet, you could potentially get exposed to virions and things like that, but it takes more than one to actually infect you. But the further you are away, then the amount that you may get exposed to and the likelihood that if you do get exposed to it, they might actually not be active virions, that obviously that increases as you move further away. So we're actually looking at very complex particle models, and that's what we see as the way forward to actually modeling this more accurately in future.
James, does that answer your questions?
Yeah,
Yep.
if I may
Thanks.
add a little bit. To add to what Andy and Reese mentioned, there are also different control strategies for the HVAC system that we can use to better ventilate a building, to make sure eventually we will have not that much particle or COVID particles in a building. And we are doing some studies and research in that domain as well, to see how and if those control strategies for HVAC system can help us with this.
So I want to build on the question a little. I think this is mainly for Andy, possibly also for Nastran. In the images that you showed, you were working mainly from streamlines. And it strikes me that we've talked about using streamlines now, or particle models, or concentrations, and streamlines have neither the capability to show diffusion that you have with concentration, or the decay that you have with that you could have. So why did you choose to use streamlines?
So for me, it was just purely looking at, is there air being moved across the tables, and then where is that air going? So we have, as I mentioned, with other models that we've looked at, we have looked a lot more closely at particle models and these scalar models, with the aim of seeing what is the potentially the local transmission around the space, the particles, where do they go? And the reason why we did that with those other ones is because in this case, with this particular model, with the restaurant, we had full control over where the extraction is. Whereas when we're looking at some of the other spaces, like you're walking into an office that's been around for 50 years, we're not going to really be able to change the HVAC system. And so then we start getting really interested in, where do the particles go from this desk to the other side of the office? Does that happen? And in a lot of cases, yes, there's air going across from one side of the office to the other. And that's when those particle models get very, very interesting in this case. We know the particles, the heavy droplets, they will always go to the table in front of you. The lighter ones, the aerosols particularly, will then get carried by the air. So with the streamlines, we know that they will follow the streamlines. And so we know that they're coming out through the extraction.
Okay, thank you. Here's a question coming in from Eric on YouTube. And this is at Nastran. He'd like to know if you've experienced or applied the tools that you showed to natural ventilation, and if you could share any details on that.
Okay, so I would like to first answer the previous question about the streamlines. The streamlines were used for part of the analysis in that study, but for that work, we used transient turbulence analysis. So we do have temporal as well as a spatial information about the temperature and airflow. And the study that I presented was one part of a series of studies. So what I'm trying to say is that those information about time series and how the temperature and air velocity changes can be used in aggregated form or be analyzed during time to understand different aspects of the airflow and temperature changes. And for the ventilation and natural ventilation, that was a very good question. This is an interesting field. No, unfortunately, I did not have the chance so far to work on this, but this is an area that we are looking into as well, because there are lots of interest and there are lots of potential to save energy, as well as to provide good ventilation for people in buildings. Yep.
All right. Thanks. And Nasser, I've got one more for you, and this is from another Eric who's watching us on YouTube. Did you consider the supply and return in the ceiling, which is very common? And he suggests that case could better match the mixed zone assumption that most energy models use.
Well, for this study, we did not use the location of the vents in the ceiling, but that can be added, and it would be an interesting study to compare these cases. For this one, we did not include that.
All right. And got a question coming from YouTube, and I think I'll address this to all of you. What CFD software do you use, and is it available for everyone to use?
So with my models, they're all done through Autodesk CFD, and yes, that is available.
For my case, actually, I use OpenFOAM, and it's an open source software that everyone can use. So the interface is not. It may need a little bit of work to get things running, but yeah, OpenFOAM as well can be used for this analysis.
Yeah, and we, for the multi-agent project, we didn't use CFD. We hand coded a simple diffusion model. But you saw a video at the end where we did have some particle flow. That was just that was using Andy's simulation with the Autodesk CFD solution, and then combining it with some of the human behavior visualization techniques.
All right. We've got a question coming in from Gokul. Gokul, do you want to hop on your mic and ask your question?
Sure. I had a couple. First, great presentation, guys. Thanks so much for presenting. My question was for Reese. With the three models you were describing, the COVID model and the behavior model, were they all modeled using the same simulation software? And was the dashboard kind of something you did, or was the software, did the software, show up or give a dashboard at the end of your modeling?
Yeah, so for the multi-agent project, everything you saw was basically hand coded, more or less from scratch. I mean, so there was no, available simulation tool that we took to do the multi-agent simulation or the airflow. I suppose, I mean, there are some tools available, like LBNL has a multi-agent occupant simulator, so that might have been an option. I don't know if it has the same. You saw how detailed the model was. There's not many that have that level of detail. But basically, everything you saw was sort of custom coded for this project, as a proof of concept.
Yeah, thanks. I'm aware of the LBNL simulation tool, and they're not as detailed, so that was why I was interested in what you guys were using. So thanks for that. My second question was around your data sets for the COVID model, and also, so where did you obtain it? Was it publicly available? And what degree of uncertainty do your models have because of the COVID models, and also with the simulation of occupant behavior?
So they have a very high degree of uncertainty right now, because this is fairly new, the ability to trying to simulate the risk of transmission at a building scale at different time intervals. I mean, you'd see some highly detailed simulations in the literature, but they really just focus on a very contained scenario. Like they'll focused on one classroom, for example, where everyone's in a certain position, or they might focus on people, I don't know, doing some kind of exercise or what have you. So it's fairly rare to do it at this scale. I would say there's a lot of uncertainty right now. I wouldn't want anyone to think that the numbers we're getting are highly predictive, but I think we did show this to a variety of stakeholders. We showed it to business owners, people that like ran pharmacies, for example, and it gave them an opportunity to see, well, like, this is how the virus could spread, or this is like the potential impact of a sneeze is actually really high for everyone in the space. And we also showed it to health experts who commented on the potential for this kind of a system to help people to make design decisions. So I think that there's a case to be made for this kind of approach in comparing different design options and getting a sense of what the risks are. Hopefully we can refine it from a quantitative point of view. And you asked about data sets. We mostly just looked at the literature, different COVID-19 models from the literature and the parameters that they used. So for some things like the half-life on surfaces, they've got very good numbers, but for other parameters like diffusion and stuff, it's very hard to get accurate numbers. But if I wanted to say, like, there is potential to look at data sets. For example, we could get data sets for events in the past where there was an outbreak or a super spreading event, and you could compare it to these scenarios. So there is the potential there to use these historical data sets.
Thanks, and great graphics throughout the presentation.
All right, yeah, thanks. And speaking of graphics, here's a question coming from Salam on YouTube. He says he's fascinated with the computer graphics that were used to represent the grid. And also, what program was used to illustrate the grid and the dashboard that was developed?
Yeah, so we used Unity for most of the visualization. We wanted a game engine environment because we wanted to sort of feel like a game engine, especially for users who maybe weren't that knowledgeable about the virus. I think health experts said they'd sort of prefer just to run thousands of simulations and look at the numbers. But we wanted to go for that game experience, so that's why we chose Unity to prototype that quickly. There's a variety of approaches we could have used, though.
All right, thanks. We've got one more question. It's also coming from Eric on YouTube. Can the speakers answer if Autodesk is planning a replacement for Autodesk Flow Design? Anybody know?
I wouldn't know. I don't work in products.
Unfortunately, I don't have the answer for that too.
Eric, maybe you'll have to reach out to someone else to find out the answer for that. Well, I'd like to thank our speakers for this great presentation today. It's really been very interesting to see what Autodesk is doing in terms of modeling for thermal comfort and for COVID. I want to thank everyone for joining this IBIPC USA Research Committee webinar. If you enjoyed the webinar, please consider joining the IBIPC USA Research Committee. Email research@ibipsa.us or visit the link in the Zoom chat for more information. For those of you watching us on YouTube, please like this video and subscribe to our YouTube channel. And finally, please join us on July 29th at noon Pacific time when Anthony Fontanini presents end-use load profiles for the US building stock, residential stock model calibration and validation. Thank you, everyone.